processes are a part of a series of other processes which comes later. If we see how first you got the raw material, so that process you have to understand, then only you will say, okay, I got the raw material, I got somehow a product which is not of exact shape and size, so now I have to go for machining and other things. So first, once, so first what we have to do, we have to start the thing with some raw material, and then we will go for the manufacturing processes. So let me share my screen, then we will continue our discussion. Uh, can you see the screen, the
Yes, sir.
presentation part?
Yes, sir.
Okay, okay. Now
Yes, sir.
see, this class is related to foundry practices, and since foundry and casting is interrelated, so we will have some basic idea related to casting, and then we will have a detailed idea related to the foundry. So those parts you are well acquainted in day-to-day life right from the beginning. If you see any of the products related to your household things or in industries, lot of casting products has went through you, but since you do not know that these products have been made through casting, so maybe you are not aware. So I think you did lathe lab. Okay, so lathe means turning lab you did in turning center, and there you find out the lathe machine, and that lathe machine bed is made of casting, as well as other very other components also. If you see a chassis of an engine, that is made through casting. So if you know a basic of casting, you can admire how casting is there in your day-to-day life. So that's why we are calling it as the first step of manufacturing. Cursor is also visible to you, na students? Cursor is visible to you?
Yes, sir.
Anyone?
Yes, sir.
Okay,
Yes, sir.
Yes, sir.
okay.
Yes, sir.
So this foundry and casting is the first step of manufacturing. Like it will provide you the raw material for machining center. Got it? So for that, if let's say if you do not concentrate on casting and foundry, and you generate some raw materials which has got, as I told you, which has got very defects, then what will happen? That defects will replicate while you doing machining, and you will have high cost incurred in the process of manufacturing. And since we have to keep the process economical, so what we have to do, we have to make casting as fine as possible, so that it will be easy for other processes to take up. Okay, so this casting and foundry is the most primitive manufacturing route. Like from right from the beginning, people started to think, okay, what we can do, we can put a shape and size, a cavity, and there if we pour some liquid, we will get the desired shape. It's fine, it looks very simple. But right now, if you see the manufacturing aspects of casting, it has went a long route. So why? Because now you have to understand that the properties of the cast material can be tailored if you obtain the practice of casting in a proper way. Thus, people started to think like how we can do it. So they made some procedures. That procedures, if we follow, we can get a good cast product. Now, just a common definition of casting. What is casting? Casting is a manufacturing process. This is okay to you. What we are going to do? We are going to pour a liquid material in a mold cavity. Now, that mold cavity has to be made with some material. Okay. Those materials we will study how we can make a mold cavity. Mold cavity means a cavity which is surrounded by some material. In our case, it will be green sand. Okay, and that cavity, if someone will ask, okay sir, how we will make that cavity, so we will say, okay, we will have a replica of the actual product that we want. We will put the replica in that sand, and that will make the cavity. So that replica is called as pattern, as I told you in the initial discussion. Now all these practices takes care in workshop, whose name, what we call it as Foundry. Okay, so Foundry process basically involves making the mold and the core, and melting and pouring the melted metal into the mold, and finally removing the mold and the core and finishing the product. Finishing the product requires other activities also. Up to here, we have to discuss in this class. Now, this again shows you the definition, and after definition, we have shown you a cross-section image. Why this image is important? If you see, maybe
Sir,
some of the parts.
sir, we are
Hello.
able to see the 44th slide now.
Yes, sir.
So,
Yes, sir.
okay, 44th slide.
Now the third slide is visible.
Third slide is
Oh,
visible now.
Yes, sir.
Okay.
yes, sir. Not outside.
Okay.
Yes, sir.
What about now? Is it third or something else?
Third only.
Third.
No, it is
Third.
Third
third,
only.
sir.
Okay, maybe some glitch is there. So previously also I was in this slide only. So this slide shows you a cross-section image. Okay. Now in this cross-section image, what we have tried to show you, we have tried to show you all the topics that we are going to cover in this class. What are those topics? Those topics includes whatever you see a box, big box, it has got two parts. If you see here, it is written cope, below it is written drag. So the two parts of the box, the topmost part is called as cope, whereas the bottom part is called as drag. So these two words will come into picture when we will see the video also. So you should have an idea what is the name of the parts. Now this section, you see white section where cavity is written. This cavity is the actual desired shape that we want. Okay, so only this much, this cavity. But liquid metal has to reach up to here. For that, what we are doing, we are providing a path. This is the path through which liquid metal will flow and will finally fall into this cavity and it will fill it up. So this path, we call it as gating system. What is the name? Gating system. It starts from here. This is the portion from where you will pour the liquid material. So it is called as pouring cup. Once it flows through a vertical channel, it is called as sprue. Okay. Now, after passing through this vertical channel, this horizontal part is called as the runner. And finally, there will be a gate and material will fall. Now, someone can ask, okay, so we understood these topics. This is the gating system, this part, and the topmost part is scope, the bottom part is drag. This is the part that we want to make. What about this one? So this one we call it as riser. Okay. And the need of riser, why we are giving riser, those will come in next slides. But try to keep in your mind while going through the slides, these words will come. The drag, the bottom part drag, the upper part of the mold, cope, the cavity, which has been made using a pattern, and this system of pouring cup, sprue, as well as runner that will constitute the gating system, and one more product called riser. Okay. Now again here, okay, this has been made in animation point of view. Okay. So this is a flow chart. Can you see the flow chart now, students?
Yes, sir.
Yes,
There
sir.
is a flow chart. If you see over here, what this flow chart suggests, it suggests how you are going to do this casting process. So you have to make mold. What is mold? This dotted zone, all this dotted zone having cope and drag, those are filled with sand. For your experiment, it is green sand. So that preparation of sand is one of the steps that will help you in mold making. Pattern making means this cavity you have to make, so that replica you have to prepare. That comes under pattern making. Now core is a part, central part, that you keep inside if you want to make some hollow surface. So core making if needed, that is also comes under picture. Once you do this, you will have a mold and you will have a cavity. Now from raw material point of view, you have to melt it. So how you will melt it? You will melt it somewhere where the temperature is very high. Up to what temperature you will melt it? So you know every material has got a melting point. Let's say if we talk about aluminium, it is around 640 degrees centigrade. So you heat it above its melting point. Once you melt it, you bring it and pour it in the this cavity. How you will pour? Through this pouring cup. Once you pour, it will start solidify and cooling. And once the solidification gets complete, what you will do? You will remove the sand mold. We will clean the final product, and we will see what happened, like what sort of defects are there. So these two images basically shows you two different type of cavity. This cavity is in the cope, okay, while this previous cavity is in the which part? Drag part. So try to understand, one is in cope, another is in drag. So when it is in cope, what it is written? Using self core pattern. So self core pattern is not explained to you. We will explain this. Then you will understand why we have kept it in cope, and the simple pattern, solid pattern, we have kept in drag.
Excuse me, sir.
Huh?
So,
Ask.
sir, actually, I did not understand the drag and cope, sir. So, in this diagram,
Okay.
it
See,
is
there is a
shown.
ask.
So, it is shown only to a vertical line that has some blackened.
No, no, no. That is not. Basically, this is a box. Okay, you are seeing a cross section image. So if it is a box, this box has got wall that has been hatched over here, but this dotted zone is filled with sand. And if you see, there is a center line called as parting surface. Okay. So basically what we are doing, we are making mold in two half. This half can go out independently, and this lower half can go out independently. So the upper half, we call it a scope, and lower half, we call it a drag. In We will go in the video, because what happens na, if I directly go into video, you will face problem to understand. So let's finish some of the slides that is required to understand the video, then we will go in the video. There again you will get some common things. Once you complete those, and I will give you again time. If you want to ask, you can ask in between also. If you face difficulty to go in other slide, then you can ask, not an issue. We have
Hello.
sufficient time, huh?
Actually, the other picture is not visible. Sahid sir.
Which one?
The other
Which one?
picture, that is the pattern is in the drag, so that picture is not visible. So I have put an
Oh,
animation. That's why the doubt is coming.
okay,
So
let me see. Oh,
so
there
you
is
just
animation. Now it
yes.
is okay, it is visible. Hello, Ipsita.
No, it's not visible.
Okay, so we will show you again. Mm, okay, no issue. After video, if you face the problem, we can again come to this slide number 3. Okay. Now,
Excuse me, sir.
mhm,
Excuse me, sir. Sir, can you please
uh,
show the slide 3 once? I have a doubt in that.
okay, slide. So this casting and foundry is okay. This slide.
Yes, sir. That's okay, sir.
In this one, can you see the image now?
Yes, sir.
Okay, just ask me if you want to ask something related to this slide only. You want to ask,
No,
student?
sir. The before slide which you have shown.
Before.
Slide number 3.
Yes. Slide number 3. Yes, sir.
Slide 3. Okay. So this is slide number 3.
It is not coming.
Visible,
Yeah.
sir. Yes, sir. Yes. Sir, can you please show the cavity with the cursor? So I can't understand
Yes.
where is the cavity.
This one is the cavity. You can see it's written over there. Na? So this comes over here, this white portion.
Sir,
Got it?
after solidifying, sir, after hello,
After solidifying.
the shape of the shape of the item will be like the trapezium, like the like that shape itself.
Yes. But in center there will be a hollow portion, blind
Okay,
hole.
sir. So
It is like
so
inverted cup.
yes, sir, inverted cup.
Yeah, inverted cup. See, once you make something, if you can do this casting in inverted way or in direct way, there should be some logic. Okay. So once you get the product, it will look, you can keep it straight only. But you are doing casting it in the inverted form. Why? Because you want to make this core, this we will call at self core, with the help of sand. So that should be there, and because of that, we have made it in the inverted form. Let's see the video. This thing is very clear in the video. Okay.
Sir,
So I
that
think
L shape, how
that L shape.
you have wrote the pouring cup, no, sir?
Yes.
So from there itself, we should have to pour the liquid. I
Liquid
mean that
material. Correct.
liquid part. So how it will reach the cavity, sir? Then
How it will reach? If you see this path, after pouring cup, what we have the second part? Screw.
yes, sir.
Then comes through runner. Okay. Runner here, there is a channel. Okay. Through which it will fill this cavity.
Yes.
This is a cavity, and there is a gate after runner, and through this gate it will fill this cavity. Got it? So Ipsita, can we play the video right now? Because I think students will understand easily if they will see the video.
Okay. Before that, show some
Uh,
application part.
Because lots of slides were there, so we thought we should complete some of the slides, then we will go for the video. Anyway, okay, let's move on to the
Okay.
next slide. Okay, have some three or more slides, then we will go in the video. So now classification of casting. So I told you what we are doing. We are doing casting with the help of mold. So that mold can be a permanent or on a temporary basis. Temporary means once you make a product, you can break the mold. You can again make a new mold and go for the casting. But in permanent mold casting, that mold will not break after each and every cast product. You have to keep it. And how this will happen? This can only happen when the mold material is in such a, you can select a mold material which has very high melting point, and the cast has got relatively very less melting point, so it will not hamper the material, as well as it is easy to take out the material from the cavity. Okay, if you can take out the material without breaking it, so it's okay, you can keep the mold. So in that basis, we have two types of mold: expandable and permanent. Expandable, basically we are using green sand casting, as well as there are other mold also, like CO2, sodium silicate molding, investment casting, etc. In permanent, we have in continuous casting, ingot casting, strip casting. So these are the casting process that basically industries follow for continuous or large batch of products. If you see the rail bars or the cross sectional square bar that is coming out from a steel plant, that comes through continuous casting process. So this casting process has got a permanent mold. They are not always breaking it. Now microstructure and properties, these are basically like depends on material. This part is a common part. If you know that materials are crystalline, so their atoms are arranged in a particular fashion. So if that fashion, once you melt it, that gets distorted. During solidification, they again start forming their structure. So that process basically decides what sort of microstructure will be present and what will be the implication of that microstructure on the strength of the material. Now, since previously I told you the casting can be divided in two parts based on mold. Now, based on the raw material that you want to cast, we have two types of casting. One is ferrous, based on iron and steel, and non-ferrous like copper, aluminum, etc. For your class, we are going to cast a aluminum-based product. Okay. Now see the applications like uh, you just see the size of the product. If it's a dental implant, it's very small. Okay. If it's a pump housing, it's quite big. So the range of applications of casting is quite vast. The product size varies from very small to very large. The product quantity varies from few numbers to many numbers. Okay. So it has got a lot of applications. Even if it is a primitive process, why we are going to make so many products using casting? Just because, just because, please mute your mic. Just because,
काम करिए पहले आप मॉड्यूल ज्वाइन करिए just join the modules these both are the
please mute all of you. Okay, so these products has got large variations, but still we are going to go for casting because it is what? It is economical. It is practically giving you your desired product at a affordable price. So we are going for casting. These are again some of the applications of aluminum casting where the wheel base is made through casting, the piston head, engine block, all these parts. Now, if I ask you how you get raw material for casting, sorry. So in that case, you can say, okay, sir, we know about mining of metals, mining like iron ore mining, aluminum mining. From there, we the oxides of the metals are present, and we are doing the some distillation process, and finally you are getting the final raw material for casting. As well as we are recycling also. So in casting, we can use the recycled product after purification, obviously, and we can use it for making another product. So this is also environmentally, it's a good aspect. Okay, you are recycling the materials, and that will decrease the loads on environment. Now, metal processing. This is a common step, like to make you understand how other processes are related to casting. So casting, basically, we are using mold. We are making a product, but that product may be of not exactly what you need. There may be some dimensional error, so you can go for cutting. How you can do cutting mechanically, like you did in, I think, during lathe experiment, you decreased the length of the job. So that you did, and cutting operations are always there, and non-traditional machining is also a part where you can do the cutting process, like laser cutting. Forming, what do you know about forming? Forming means we are basically deforming the material with the help of external pressure, that you can do at room temperature also. So we called it as cold forming. If you do at a higher temperature, you called it as hot forming. And joining, you did in your previous classes, like you can join two materials to get your desired size, shape and size. So welding you did, brazing, soldering, and other processes are also there.
Sir,
Now, hello. Yes.
sir, what happens after forming?
Forming, like you want to change the shape and size without adding any material, without removing any material. Got it? Let's say you have a sheet. You have a
Okay,
sheet,
sir.
it's flat, and you want to make it curved. So what you will do, you will put it in a machine where you will apply load, and it will get deformed, like the door of your car. If you see the door of the car, it has got some shape and size. So that is not the actual shape and size that came into the factory. It was the flat sheet. Okay. That sheet, with the help
Yes.
of forming, you made in a proper shape. So forming is a process where you are not adding any material, you are not subtracting any material. What you are doing, you are applying external pressure on the material to deform it. Okay. Now, advantages and disadvantages of casting. Casting, as I told you, whatever pattern you keep in the mold, whatever pattern, that pattern may be a very simple pattern. It has got a very complicated shape. You can have 5 parts that you added in the pattern, and that pattern belongs to 5 parts. That also you can do. So intricate shape can be formed. Let's say you have to form a shape which is very complex, and I will give you, okay, do it through machining. So maybe you can do it through machining, but that will be very difficult. And maybe the damage of parts can also take place. Why? Because the shape, somewhere it's very thin, somewhere it's very thick, somewhere the strength is very low, somewhere strength is very high. So once you machine it, you apply pressure. In that case, it can damage. So, but in case of casting, that is not the case. The material is in the molten form. Whatever shape you give, it will form. Again, large varieties, I told you can have a very small to up to very large. You can select any material that you can make. And large size component is again the same point, mass production. So these are the advantages. Disadvantages, if I told you, I poor accuracy. Why? Because of shrinkage and casting defects. So shrinkage, as you know, any material that gets some temperature, any metal that you heat or you change the temperature of that material, either it will expand or it will contract. Okay, this is always there because it has a coefficient of contraction and coefficient of expansion property. It means the temperature change will change the size, although it may not be visible to you. Sometimes it's visible, sometimes it's not visible. But when a liquid metal comes into a room temperature, what what is the variation? Let's say for aluminium from 700 to 25 degrees centigrade, it's a large variation. So in that case, shrinkage means contraction of material takes place. When you heat, expansion takes place. When you cool, normally contraction takes place. In that case, shrinkage will occur. That's why the accuracy will change. So that you can take care. Obviously, you can take care through some back calculation. Okay, this much shrinkage takes place for aluminium. Give this much more tolerance or this much more size and shape to the pattern. Poor surface finish. Why poor surface finish? Because that cavity is surrounded by which material? For your case, sand. So that sand has got its roughness. So that roughness will get replicated on the surface. That's why the poor surface finish. Now the mechanical properties variation within the casting is not good. If this statement is quite like harsh, but actually the thing is you can tailor it. The mechanical property variation depends on the variation of temperature within the material molten pool. If you control the flow of temperature within the material, you can have a good mechanical property also. But that you have to go through research work, but because that's why I told you, although it's primitive, but we are regularly trying to enhance the mechanical property of the cast product. Environmental effects, it's always there. High temperature, toxic material, gases can come out of the casting. Then handling of the molten material is also hazardous. If you are having molten metal in your beaker and you keep it in hand, that's a problematic part. So that is also one of the disadvantages of casting. Now see, again, it is a cross section image showing you the pouring basin, how you will pour the liquid metal and how it will flow through screw and runner, and finally the casting cavity will get filled. And core is the part, it will come in later slides also. And this riser is given. Okay, so what we have to study, we have to study about this gating system. We have to study about the pattern that we use to make this cavity, and some few details about what is riser and what types of risers are there and all those.
Sir,
This
what
image, I
happens
think,
to the
it's
extra
more.
material that flows into the riser?
See, what you are concerned with this cavity, casting cavity. So when you flow the material, and if this riser is a blind riser, we have a riser which is open type. So that open type riser, we can see that, okay, now it's filled. It means this cavity is also filled. And when the contraction or shrinkage of liquid material takes place, as I told you in the previous slide, from where it will get extra material, this riser will assist. Whatever contraction takes place, these riser, the material from riser will flow and it will fill this cavity. In that way, that riser will
Sir,
help.
but the material in riser will also solidify.
Yes, yes, it will
So
also
how it will
solidify.
flow
Yes,
properly
sir.
into the cast?
So since you, when you will take out now, what you will have, you can also say, if you are so concerned with riser, you can also say, sir, the material in this gating system will also solidify. Is it true?
Yes, sir.
If you pour something, so all these three will solidify. That is absolutely correct. But what we are going to do, once the casting is complete, we are breaking this gating system from here. We are breaking the riser system from here. These two materials again goes into remelting stage, and again we are pouring in the new casting.
Sir, that
So
is fine, but I'm saying that if the riser solidifies, then how it will provide extra material to the cast?
How it will flow
yes,
back into the
yes,
cast if it
yes,
solidifies.
exactly. So you are raising a question that risers should solidify at last. This is the prime conclusion,
Yes,
that
sir.
we have to place the riser in such a location so that it solidifies at last. That is true, and that's why if you go for riser design, you will find that the rate of solidification we find out for this cavity, and we find out the rate of solidification for riser. We keep the rate of solidification in such a way that riser should always solidify at last. Got it? So this is the design aspect. We are keeping sometimes riser on the top. Sometimes we are giving two risers, one blind risers, one open risers, based on the requirement. So always in any casting, what we are going to do, we are putting the riser position in such a way so that riser should solidify at last.
Sir,
Okay.
how does position of riser determine the rate of cooling?
See, wherever the bulk material is lying, let's say the material at the center and the material molten material at this periphery, the rate of solidification depends on the environment, in which environment you are lying. Okay, so let's say the rate of solidification, or the part which will solidify first, it will be on this periphery, then it will grow towards center. In the riser also, the rate of solidification is in such a way that the molten material will always be present in the riser with respect to this casting cavity. So if you say how much riser provide to the casting cavity, what is the value? So risers basically account for 5 to 7%. Contraction is taking place, that's 5 to 7%, and the volume that we provide in riser is much more than that. So always there must be some liquid metal part in the riser that can flow inside it. Okay, if you see the cooling process of any material, na, how cooling takes place? Through heat loss. What are the ways of heat loss? Conduction, convection, and radiation. Now the material which is in the boundary, it conducts heat. This Q, if you see this written part, na, Q, so it conducts heat and it gets solidified first. Similarly, for riser also, it starts solidifying as casting will start solidify. It will also start solidify. But we are concerned for the casting. If a small cavity will be there in casting after solidification, it's undesirable. But for riser, if it will contract, it will give liquid to casting. The shape and size of the product in riser will decrease. We are not concerned with that. No problem. We just want to fill this material, and risers used to do that work only. Understood? Means the way the riser has been kept and the quantity that we keep in the riser, those play a crucial role, so that molten material is always present in the riser with respect to casting cavity. We can again come on the riser. That riser slides are there. So now casting is a multidisciplinary approach. Like if we are going to cast a material, we need a design engineer that will tell me, okay, this size, shape and size of the casting or the dimension can change. So the contraction amount is this much. Add this size of pattern 5% more or 6% more, so that it can compensate the dimensional changes. Now the pattern maker will take the data from design engineer and it will make the pattern. That pattern can be made through different material, and that pattern will be again given for the casting process. Now the casting engineer will design the mold and its gating system, how the heat transfer will take place, and how we can place the core, whatever is required for the process. And at last, after the casting process is complete, manufacturing aspect will come into picture, and we will do the machining, finishing, and we will inspect the material for any type of defects. And like this is the chain through which a casting can go through it. Now different sections of foundry, ferrous foundry, non-ferrous that we did. Foundry process involves making the mold and core, to melting and pouring the material, finally removing them and finishing the product. Okay, this is like the previous slide only. Now mold making materials. I told you mold we are using which sand? Green sand. So that green sand you have to prepare. How you are going to prepare? You are adding 2 or 3 materials in a particular ratio. That ratio you will mix and you will make the final product. So for your green sand mold, what you are mixing? You are mixing some clay also. Sand is already there. You are mixing some clay as binder, and you are adding some moisture in the form of water. And again, if you want to add some material for particular property, we are adding. So see, bentonite clay, how much we are adding? 4 to 10% of the sand. Water, how much we are adding? 2 to 4% of sand mixture, which activates the binder. Means moisture helps in combining sand with clay. Now some other materials you are also adding, like charcoal or other powders also we are adding for some properties. So that value is 2 to 10% of total volume. So this is what is there in your that material of mold. Sand is there, clay is there, water is there, as well as some charcoal or carbonaceous material is there. Now again, same thing, or like what sand we are using? Silica sand. Why we are using it? Is cheap and easily available. Other sands also there. See, the sand, why we are using sand? It's a ceramic type of thing, and it resists very high temperature. This we should know that it resists very high temperature, and molten temperature of material is high. That's why it's a good choice for the mold material. Binder, clay, cement, organic oil, a lot of binders are there. So this is self-explanatory. You can understand this slide. Moisture, again, water. Why we need water? So that it can act as a binder between clay and sand. Increases the blood, does reduce strength, high content, lower content, less flowability. So this is okay to you. Now molding sand property. Once you prepare the molding sand using water, clay, as well as sand, so it has some properties and some desired properties like plasticity or flowability. What is that? Once you start ramming, or once you place the sand in the box, so it should flow in all the portion of the box. That property is called as flowability. How you can assure? By applying pressure with the help of some material. We call it as rammer. Collapsibility means allowing free contraction or method to avoid tearing or cracking of the contracting material. Means when the material will start to contract, it should help it to contract. It should not get stick with the material. So that we call it as collapsibility. Thermal stability is okay because sand can withstand high temperature. So thermal stability is the requirement. That is okay because sand is that type of material only. Adhesiveness means property of the molding sand to get stick to the inner wall of the molding box. Okay, you have a box called as molding box. In that only you are filling the sand. So the sand should get adhere to it. It's not so that when you lift the molding box, sand should fall down. So that property we call it as adhesiveness. And cohesiveness means within the sand particles it should bind or attract each other. So that these are the some of the property. One more important property is, if you see out of all these, is permeability. Means it should allow the gases to escape from the molten material or from the molding sand. So that permeability should be there, because if that gases will not escape, it will get trapped within the material and it may come as a defect in the final product. So permeability is one of the important sand property. Green strength, you can go through these, like green strength, dry strength, and hot strength. All these are basically the abilities in different conditions. One is insufficient. In case of moisture, the strength should be good. when it gets dried because of the high molten liquid. At that time also strength should be good, so called as dry strength, and it should hold the shape of the cavity. The shape of the cavity should not distort in liquid state, so hot strength we call it as. Now permeability, as I told you, it is one of the important. So how you can give the permeability to the material? By selecting different types of grains. So if grains is coarser, it's very high permeability. It's very fine, permeability is low. The shape, if it is very constant shape, permeability decreases, and if irregular, so
Sir, how
which
is
is,
the adhesiveness used? Means if we pour the molten metal in the mold, then how the sand particles are in their place?
see, once you pour the liquid material in the box, so what will happen? Immediately the moisture in the sand particles present in the periphery, that will evaporate. So once it evaporates, that liquid metal, that property comes into picture. Which one? This one. Like I told you, na, dry strength means it should not collapse once you place some liquid metal inside it. So the property of sand is in such a way that when it dries out, again also it can hold its shape and size. Because once you place liquid metal, what does it mean? It means the moisture will go out. Moisture will go out, then what will remain? Clay as and sand will be there. So that binding property of clay has been activated through moisture. Because it happens like that only. Once you place the moisture or water in it, the binding property between the sand and clay gets activated. So clay at that point will act as a binder between different sand particles. Okay.
Yes, sir.
So again, permeability, these are the various types, like how you can change the permeability of a material. Like bigger grain results in worse surface finish, finer grain, better finish, but permeability will be less. Like that, you can play with the size of the grain to give a desired permeability. Again, this is chart shows you this mesh size retaining sand. Mesh size means you are what you are doing, you are using a sieve to get a desired size of the sand. So that mesh size comes for that sieve. Okay, if you want to filter something, the type of size that you want to filter is defined in the form of mesh. So we call it as mesh size. The mesh size and the permeability has got a invert ratio. So we decide what much permeability we want, and for that what mesh size sand is required. Now, to go in these slides, different tools, let's go in the video, because these tools again will come into picture in the video. This now we are switching to your actual lab work, what you are going to do in your lab, because since previous batches used to do it themselves only, but for your batch it is difficult. So these tools are required for the actual experiment. So let's go in the video. There you will find these tools and their applications. Then we will come to the pattern design slide. Okay. So by that video, I think whatever we studied right now, those things will get clear. And what we will do, then we will have a small 5 to 10 minute session of question answer. If you think again something is not clear to you, we will go on that, and then we will come on pattern, because that part now we can conclude with using pattern design and getting design as well as some defects. So those three
Sir,
topics will be
please
there.
show the previous slide once more. Yes, yes, sir. This
Which
one.
one? This one.
This one. This one.
Okay.
Okay, sir. Yes.
So these are various tools which we are using. Below is one of the tools. Slicker, lifter are different tools. So the applications, once you see, then you read it, then you will understand, okay, this belongs to these. You just see the dowels. Dowels is important because these two will make way for, one is the sprue and one is riser. Okay. So for, you saw the cross section, na? There was a riser zone, there was a sprue after pouring basin. So those two will be made. Brushes, guide pins. What is the application of guide pins? We will see. These are small tools. So rammer, why we are using rammer? Why we are using a strike of bar? why we are using sieve. I told you na mesh size, how to decide mesh size. This sieve we will use to decide the mesh size. You want a particular mesh size of sand, use a that type of sieve only. So let's go for the video part now. This we will again come. Uh, can you see the video right now, students?
Yes, sir. Yes, sir.
Sound is coming.
No, sir.
Okay.
No, sir.
In this video, it shows 1 hour 8 minutes. Okay, but this video constitutes three casting mold making process. So out of three, first one we can play. Okay, the total so that we can understand what are different procedures. And for second and third, we can skip the process so that within within the designated time we can complete it 20 minutes maximum 20-25, and then we can go for our slides. Okay, so have patience, see the video. I think through video you will understand most of the things, and whatever rest is we can go for a discussion.
So there is no sound.
Sound
Yes,
is not
sir.
there.
Yeah,
So
Okay.
you
sir.
can unshare and share and turn on the computer sound.
Just 1 second. Oh, I forgot to click on this share sound. Okay, 1 second. So again, I will open this video and let it be here only. Hello, include computer sound. Hello, students.
Yes, sir.
Yes, sir, you're audible.
Okay. Now I turned on the sound.
Section. This is the initial or primary manufacturing process. With different. We start the class where we show you the different mold making processes. First, the tools that you'll be using. This tool, the first tool, what we can see, different tools that are used in mold making. The first tool that is onto the left top is a shovel. Shovel is used for mixing the molding sand with molding sand very thoroughly, lifting it and pouring it into the mold boxes or the sheet as it may be required. The molding sand, once they have been mixed and the shovel is used, it is initially put into the sieve or needle. The sieve has lots of openings in it, and when we sheet the sand, the function of the sieve is to eliminate larger lumps of the sand. Larger lumps of the sand is necessarily removed from the molding sand mixture in order to have the fine sand particles to pass so that the first facing sand that is added into the mold box, that is of fine grains, and we have a surface finish which is smooth. Smooth surface finish of the facing sand or the mold cavity will introduce or make the cast surface smooth. If I go to the next page, this particular tool onto the left hand top corner is the rammer. The function of the rammer is to compact the molding sand mixture so that they adhere with each other. And if you can see, there are two geometrical shapes. One, this area, there is a sharp edge, this is called the pin end, and the blunt end, which is called the butt end. The pin end and butt end, geometrically, the pin end has got smaller area. So for the same force that is applied for compacting the sand, the pressure that acts on the sand, that will be more with the pin end, and we require the first layers of the sand to be compacted with larger pressure, and hence we will be using the pin end of the rammer. For the initial ramming, initial layers of ramming of the mold, of the molding sand mixture into the mold. The final layer of the sand into the mold box is rammed using the butt end of the rammer. The butt end has got a circular surface area and larger compared to the pin end, and hence the pressure that will be applied will be less. One thing has to be mentioned over here, whether you are using the pin end or butt end, the pressure or the force that is applied to compact the sand, that should be fairly uniform. Uniformity in the pressure can be ensured if you apply a uniform force which is distributed uniformly over the entire molding sand mixture compaction, followed by the third, which is important, is the thickness of the sand that you are ramming, that should also be uniform. After compacting the sand, the next tool that you will require will be in the shape of a rectangular bar. This rectangular bar tool is used to make the surface of the mold box even. This tool acts by striking off the extra layer of sand. So the operation is striking off, and the shape of the tool is a rectangular bar. Hence, the combination of the name strike, the name of the tool is strike off bar. The next operation, the next tool that we will be using will be the vent wire. The vent wire has got it's a wire of thin diameter with the edge pointed. This vent wire is used for making vent holes. Vent holes is basically the name which we derive from, if you recollect, ventilators. Ventilators are meant, they are in our rooms, they are for exchange of air. So, when we pour the hot molten metal at few hundred degrees centigrade into the mold, and the mold has moisture in it, so the high temperature of the molten metal causes the moisture to evaporate. So, a large vapors are generated which needs to be vented out. So, to eliminate or help in the process of expelling the gases that are generated, the vent holes are made. These holes are made to puncture only the backing sand layer. We can't afford to puncture the facing sand, otherwise the mold cavity will have a direct connection with the outside atmospheric air. So when we go to pour the molten metal may leak out to the vent hole. And hence, care has to be adopted when making the vent holes. The depth of the vent holes is only to puncture the backing sand layer. The next tool that we'll be using is called a trowel. The trowel has got a small flat surface to even out any unevenness of the mold surface. The next set of tools that we will be using is displayed over here is a hand brush. So the bristles over here are used to clean the table, and then in order to prevent a misalignment between the two boxes. Molds are made at least in two halves. So we require two halves of mold boxes. To prevent the misalignment between the two boxes, holes are provided in mold boxes, which aligns the two boxes in positions, and this alignment is ensured by using pins. These pins are called guide pins. The guide pins necessarily help us not only in guiding or preventing misalignment, it guides our hand movement when we go to place one box over the other. The next set of tools is called the dowel pins. This is the these are the screw pins. One is a screw pin, one is a riser pin, the other is one is used as a riser pin and the other is used as a screw pin. The riser and screw pins are, the function is, the riser, it is the screw hole through which we will be pouring the molten metal, and once the molten metal gets entry through the screw hole, it connects to the mold cavity through a horizontal passage, which we call it the runner. The molten metal now goes to fill up the mold cavity, and after filling up the mold cavity, if we continue the pouring, which we have to do it, so the molten metal now starts rising to another hole which is placed over the pattern. And since the metal in this other hole rises to the other hole, so this other hole is called the riser pin. The other tool now what we have is, you can see, is a metallic iron tool with the end pointed in the shape of a spike. So, and it is used for withdrawing the pattern out of the mold. This tool, since it is used for removing the pattern out of the mold, so the purpose is withdrawing the pattern, and shape of the tool is spike. So from the word withdraw, the word draw has been taken, and from the shape of the tool, the spike, and the tool is called as draw spike. Next, this is the slicker and lifter. The slicker has got one end, this is the curved end, and this is the flat end. The curved end and flat ends are used for finishing the molds, while the flat end is used for cutting the runner, while the curved end is used to cut or generate the pouring cup in the mold box. Lifter is another tool which is in the shape of a L-shaped tool. It is used, as the name suggests, it is used to lift. It is used to lift the molding sand from the runner. The next tool that we will be using is the bellow. The function of the bellow is to blow air into the mold cavity. A gust of air at a high speed is directed into the mold cavity. So any loose sand particles which are there or which has accidentally got entry into the mold cavity is blown away by the high air blown with the help of the bellow. Next we come to the patterns. These are the different types of pattern, and as you can see, there are three concentric cylinders of reducing diameters, one placed coaxial with the other. So this particular pattern, it doesn't have any gravity in it. It comes as a single piece. So this pattern is called as a single piece pattern or a solid pattern. Next, this pattern is what we call it. As you can see over here, for this particular view, we are not able to view the cavity that is there present in the pattern. It appears as a solid piece, but then since it has a cavity, so it is going to generate a cavity in the cast object. The casting will necessarily resemble this particular shape with a cavity in it, and the cavity will be generated by some sand in the molding mixture. This sand, since this cat corresponding to the cavity, it goes to generate a hole in the casting. So, and this is what we call it, the self-poured pattern. Next pattern what I am showing you is this is the split pattern. As you can see, there are three coaxial cylinders. One, a larger diameter, the largest, which is shown in color red, and the two ends, cylindrical diameters, they are the black color cylinders. This black extensions, cylindrical extensions, they are called the pore prints. In order to make, once we open out the pattern, you can see the two halves of the pattern. One half of the pattern has holes and the other half has got mating holes. These are called the dowel pins. These dowel pins are necessary to prevent any misalignment between the two halves of the pattern. When this pattern is used in the mold making, it generates three mold cavities in the mold corresponding to these three geometrical shapes. One one cylindrical shape will correspond to this large diameter of rate and two smaller cylindrical shapes of lengths to smaller lengths. These are the footprints. What we will be using is an extra sand mass which has been made separately. The sand mass will be necessarily of a shape of a cylinder, solid cylinder, whose length will correspond to the length of this from this end to this end and whose diameter will correspond to the diameter of the black cylinder. So we will be having a solid cylindrical sand mass, and now into the mold cavity we will be placing the solid sand mass. And then after withdrawing, before we go to place the solid sand mass, we need to withdraw the pattern out of the mold. So once we withdraw the pattern and we place, now we go to place the solid cylindrical sand mass. Once we place the solid cylindrical sand mass and close the mold boxes together, one over the other, means the drag box is down at the bottom and the core box at the top, we will be left with a annular space in the mold box corresponding to this red color cylinder. So now what we have in the mold cavity is centrally there is a sand mass supported by the two black cylinders, and around the solid sand mass there will be an annular cylindrical space. So when we pour the molten metal, the molten metal is going to take the shape of the space and it will resemble the shape of a hollow cylinder. So this type of pattern is called a split pattern or a pattern which is a core in it. Thank you.
Okay, students, can you listen to me?
Yes,
Yes, sir.
Yes, sir.
Okay,
Yes,
so
sir.
up to here it
Yes,
is
sir.
okay to you. I think he explained you three types of pattern that we are going to make today, and the last one that he showed to you, this one, this red and some black part. The actual casting of this pattern he will perform in the other parts of the video. One thing I want to make clear to you, you understood this difference, na? This black color part and the red color part. Basically, this red color part is our requirement. Okay, it is a cylinder, but it's not a solid cylinder. It has got a hole, throughout hole in the center. So it's a annular cylinder sort of thing. So how you will make that hollow portion? You need to place something inside it that will occupy that space so that molten fluid will not fill. So this black portion, the length of this, what we are doing, we are making a sand structure of this dia and this length. Okay, and once there is a cavity, you are removing the pattern. Then what we will do, we will put that sand part over here. Since the cavity has been made with the help of pattern, so once you place that sand part, it will act as a core. Core means center part. Okay, now sand part is there in the center, so there will be no liquid in this center part, only the periphery part, the liquid will flow up to this much thickness. Got it? So what we will get, the final product will be a cylinder with a hollow central portion. Okay, see the other parts of the video and just try to understand. Now I told you three parts, so this will be the first part, using one of the simple patterns. Then second, third, subsequently we will skip those parts. We will only pick the important points.
To be the first mold making operation. First, this shows the assembly of the mold boxes. One.
See these two parts you can see right now. This top part we were calling it as scope, the bottom part we were calling it as drag. So this is molding box. I showed you a cross section before. That cross section was of this box only, in this plane. Okay, if you cut these two boxes in this plane, let's say horizontal, so in a you will get that cross sectional image that we showed initially. So just see how they are making the mold and how they are using the pattern.
At the bottom and the other at the top. The bottom box is called the drag box and the top box is called the scope box. Initially, to start the mold, we place the drag box in an inverted position. And after doing so, we place the solid pattern. The solid pattern. Why it's called the solid? Because it does not have any cavities in it. The solid pattern is placed inside the mold box, little bit offset from the center. And thereafter, after placing the pattern, we put a fine layer of sieve sand into the mold box. The purpose of adding fine layer of sieve sand is to have the pattern covered by fine grains of sand. So this fine grains of sand, when compacted, will give a good surface finish of the mold cavity. We are intentionally eliminating out the larger lumps of the larger lumps of the sand particles, and thereafter, and thereby adding or filtering only the finer particles. Now, when this finer particles of the molding sand mixture is compacted, it gives a good surface finish of the mold cavity. And a good mold cavity surface finish ensures that when we go to add molten metal into the cast surface of the mold is smooth. So the first reason why we add the fine sieve sand is to have a good surface finish of the casting. Now, this layer of the sand, when compacted, it is this layer which comes in contact with the hot molten metal. And this is the layer which faces the hot molten metal. So this layer of sand is called the facing sand. The sand particles now, as we can see, is first distributed evenly, and then we are going to start compacting the mixture. The reason is these sand particles, they have on their surface a layer of binder with moisture on it. They have the stickiness property, but until and unless these particles are compacted together, they won't bond with each other and hold together. So the first layer of the sand is compacted, that means the facing sand is compacted. How? We start the ramming from the inner edges of the box and then gradually proceed towards the pattern. When we try to compact the sand mixture, we always try to maintain a uniform force so that the extent of compaction over the entire surface of the mold is fairly uniform. After we have compacted the sand, the first layer of sand, we now do add directly the sand from the molding mix. So this molding sand is not sieved. The purpose of this sand is called the backing sand. The backing means providing support. It provides support to the facing sand layer. This sand does not come in contact with the molten metal, and hence it doesn't have any function as far as the surface finish of the casting is concerned. Hence, we directly add the sand. So here you can see that again we are adding another layer of backing sand into the mold. We intentionally keep it clear, and thereafter, before we start ramming, we distribute the sand uniformly, and then we start ramming with the other end of the lama, which is the blunt end of the lama. This blunt end of the lama is called the butt end of the lama. The reason is we'd like to have a uniform surface. But despite having rammed it, we don't end up with a surface which is flat enough. Hence, to make the surface uniform, we need to strike off the extra layer of sand that is projected on the mold. The tool that we use for removing the extra layer of sand is in the form of a rectangular bar. The function of this tool is to strike off the extra sand. Hence, the tool is called strike off bar. This operation gives me a flat surface on the other side, that is the drag box side of the mold box. After using the drag cycle bar, we use a tool which we call it the vent wire. The function of the vent wire is to make the molds, the mold makes holes in the mold. This will enable or this will facilitate the escape of gases from the mold when we pour the hot molten metal into it. Hot molten metal, when it is poured into the mold at around 800 degrees centigrade, causes instant evaporation of the moisture and decomposition of the mold binding material. So the gases that is generated at the high temperature, they need to be vented out. And the venting of the material, of the gases from the mold, is facilitated by making the mold having holes which are not deep enough. They go only to puncture the backing sand layer, but doesn't go to puncture the facing sand. Had they punctured the facing sand layer also, it would have led to the leakage of molten metal through the fine holes. So these holes, their function is to help in the escape of gases from the mold. We call this property of the mold as permeability. Now we have inverted the mold box. This mold box, the drag box, it has certain impressions of the table on its surface. So we even out the uneven portions of this and make the surface even by using a tool which we call it the trowel. After we have leveled the surface, that means the surface on which the other box is going to rest. That means the parting surface between the two boxes, they are leveled out. We are going to place the other half of the mold box. This other half of the mold box is going to come and rest over this lower box. That is the lower box, means the drag box. So when we place the other half, that is the second half, that is a cope box, we have to prevent the cope box from getting displaced with respect to the drag box. And how do we prevent that? We use guide pins. These are the two guide pins. One of the guide pins have been placed into the hole and the other half of the other guide pin. This prevents a misalignment between the two boxes. After doing so, and before we add a fine layer of the facing sand again, we sprinkle a layer of dry sand on the surface or between the two, or on the surface of the drag box. This dry sand layers deters the two boxes from adhering with each other. The layer of sand that we have in the drag box, it has binder in it, and the other layer that we are going to add is going to have binder. So when we compact the two boxes, the sand in the two molding sand in the two boxes, they are obviously going to stick with each other. To prevent the sticking of the boxes between the molding mixtures in the two boxes, we sprinkle this dry sand. So this dry sand helps in the separation of the two boxes. Hence this dry sand is called the parting sand. Once we have sprinkled dry parting sand over the parting surface, we are going to next place the provisions for introducing molten metal into the mold. One of the pin is placed over the pattern, and this pin which has been placed over the pattern is going to serve the function of a riser hole. We'll explain in the subsequent class what is a riser hole and what is a sprue hole. In this function, the other pin that we have placed away from the pattern, that is called the sprue pin. That is going to generate the hole through which we'll be pouring the molten metal into the mold. After we have done so, we are going to have the fine layer of sand again sieved into the box. Why again we need to have a fine layer of sand? Because this layer of sand also is going to come with the hot molten metal. It constitutes the other surface of the pattern. Hence, this surface of the mold box also needs to have a good surface finish. And in order to have a good surface finish, we only use fine particles of the sand. Now, after doing so, we will try to make the pins stand straight or erect by pressing the sand around the base of the pin with the fingers. And after we have done so, for both the pins, we are going to compact the mixture. Compaction of the mixture is done by an action which we call it the ramming. The tool which is used is called the rammer. The end of the tool has got two different shapes. One is the sharp shape and the other is the blunt shape, as you have seen for the first box. The pointed end has got necessarily a smaller area. Hence, for the same force applied, the pressure that gets applied onto the sand, that is more. So the pin end of the rammer is used for.
Okay, students. Up to here, what he did in the cope box, he put two pins. One is for sprue through which you are going to pour the liquid metal, and he has to make a channel between this sprue up to the cavity, and this is the riser that he has placed above the your pattern. So up to here, now it was different, but now he will again put the facing sand like he put, and then he will do the ramming process, and then he will put the backing sand, and then using the strike off bar he will remove the extra material. So those parts I will skip, and let's go to the next part. Okay.
Initially round the sand box and will gradually come
Sir, please
towards
go.
the center, directly adding next unsieved layer of sand. The unsieved layer, the backing sand getting added. But then on the edge of the box, action of the sand, since you have some depressions in the mold, it is the unsieved layer of sand. And now, as you can see, the butt end of the, you call it, strike the dentos went wire. Look neat, going to clean, separate out the top so that.
Okay, he did the venting process. Now he will remove these pins and see the next process now.
It becomes neat, and we don't have any sprinkle bar molding sand. After doing so, we would separate out the two boxes. On separating out the two boxes, the part of the pattern which is embedded in the drag box, that surface is visible. This pattern needs to be removed from the mold box.
This depression has came because of the pin of sprue, and now we have to connect this. We will remove this pattern. We have to connect it using some gate arrangement. Okay. So see how he used to do it.
Now, we use a tool which has a pointed spike end. And the tool is used. This is the tool which is being used. It has a pointed end, and now it is rammed into the pattern, and thereafter it is rammed from the side to make the hole or free the pattern out of the mold. After doing so, we very carefully and slowly will lift out the pattern. Thereafter, thereby we generate a neat, clear impression of the pattern in one of the box. This particular box which you can see, this is the drag box. After making this, with drawing the pattern, we have to cut a channel that connects the end of the sprue pin with the mold cavity. This operation is necessary so that the molten metal that is poured through the drag box, through the sprue hole, finds a passage into the mold cavity. The tool that we have used initially to mark that shape, a tapered shape, that is what's called the slicker. And after the slicker has been used carefully, care is taken to use another tool to lift out the sand mixture from the mold box. This tool is what we call it is the lifter. Why is it called lifter? Because it lifts out the sand mixture. Care is taken to prevent any loose sand from getting into the mold box, into the mold cavity. Not only care is taken for preventing, we have to ensure that there are no loose sand particles into the space.
Okay, this completes your first of the first part of solid pattern. Now they will go for self core pattern. If you remember in the initial starting of the class, one of you were asking about that self core, how it has been placed in cope. Uh, what video we saw right now, there the pattern was placed in which part, cope or drag part. Now in this second, we are going to place it in the cope part. So there is a difference. Just see the difference and we will skip the video.
We initially take the mold making with self-port pattern. To start the mold making, we initially take the self-port pattern and place it along one of the diagonals.
So this box is different what we saw in the previous video. This is a cope box, means the topmost part, and that in there whatever we took was the drag box, means initially we worked on drag then cope, now we are working on first cope.
With offset from the center of the mold box. After doing so,
Let's
and
start.
place it along one of the diagonals, little bit offset from the center of the mold box. After doing so, we place the screw and drive, which is placed over the pattern that serves the purpose of the riser hole. The other pin, which is placed away from the pattern, that to lie out from the into the mold box, ensures uniform texture. That means a smooth surface. Now, if we put a little consideration that it becomes hot mold particles. So filling of the we had put the backing sand. Well, the first end that we have used in the after compact is you can see is to strike off the external sand. And what is the shape of the tool? So hence the first tool was joining the holes, the molds and packets which liberated. Hence they have to be liberated out. So we have used ventals. Remember one thing, we have to have these ventals which does not go to some puncture or reach the surface of the mold. Otherwise, molten metal will leak out from the mold. And hence, we use the vent wire, the tool that is used for making the vent hole, and it goes to puncture the mold cavity, only the backing sand layer and not the facing sand. We are showing you the holes. What is this hole that we have just now? You can see clear. That's called the screw hole. Why screw hole? Because that is the hole through which we will be pouring the molten metal.
I think sound and video, those two are playing at different time, na?
Next, we are going to place the other box. This box out of it we have put, that is called the drag box. And the initial box into which the sand that we compact in the drag box does not draw a bond with the box of the compacted sand in the cope box. The reason is the box in the first bottom box as it's in the drag box does not draw a bond.
1 second, huh?
Excuse me, sir.
Just it,
Sir,
tell me.
Sir, how do we differentiate between drag box and cope box? Means how do we come to know that which one is
The top portion is cope 1. See, there are two parts, na, top and bottom.
Yes, sir.
The top box is see, both are same. The top portion, can you see the cursor now on the video?
Yes, sir.
So this part, top portion is cope or drag, but here it has inverted it. Okay. What we are going to understand, if you are making it cope, you keep it in mind that you are working on cope box, and this basically is an inverted image that he has shown. For filling, you can put it in any way, but for pouring, when you will pour the liquid metal, at that time you have to understand which one was core and which one was cope, which one was drag. And how you will understand? Let's say here you will make a gating system, you will always pour through that gating system. Okay, so that gating system will lie in the top part always. So that top part is corresponding to cope box, and bottom part corresponds to drag box. You once he complete this video, na, you see where is this cavity which is now below. After completion of this cavity, which is now at the lower part, what he will do, he will invert the box. So what will happen? This will come up, this will go up, and this will go down. So this will become cope box.
Okay, sir. So means the top part from which we are pouring is cope.
We are pouring from top part. Okay,
sir.
So just see how he will invert it. For making this mold, you can turn it in any way which is suitable to you. But for pouring, we need to be in such a position that cope is on the top and drag is on the lower part.
Okay, sir.
with the
Okay.
of the compacted sand
Excuse me, sir.
in the
Sir, why
Yes.
can't we pour the molted metal directly into the shape? Why do we need the two holes to do that?
See, this demo that we are showing you is the simplest part of casting. So we have a simple solid pattern and you are pouring it. You can directly pour also, but that flow of the liquid will cause some damage to the bottom portion because of the gravity effect. Okay, so this is one of the aspect. Second aspect is when you go for a complicated shape, na. So in that case, you cannot always pour through the top portion. It may damage your cavity. So for that, you need to pour it from some other place. Second, you need some position so that gases can evolve. You make some vent holes, na? So when the liquid metal will fill that portion, what will happen? The top portion will also have liquid, bottom will have the cavity if you are pouring directly. So in that case, the evolution of gas will get hampered. So what we are doing, we are pouring it from some other place so that whatever gases forms that ejects out through that molten, through that permeable sand, and we can get defect-free casting. So two or three reasons are there. One is to prevent the shape of this cavity from getting damaged, and so that liquid can flow easily. And if you want to give some directional solidification effect, na, like you want some part to get solidify first, some part to get solidify at last. Why? Because the rate of solidification will decide the property. So for that, it is easier to provide the material from through a gating system. So control is the most important factor over here. Okay.
Yes, sir.
box. The reason is the box
So
is
there is a issue, I suppose. The
the first
video
bottom box
audio,
happens
if
to
you
looks
listen,
appears now in this
see he is putting the parting sand. But what the audio is saying, let's try to understand.
configuration. That's a core box that has binding material, and the other sand now what we are pouring it that also has binding material.
These two are different. You got my point?
Yes, sir.
So
Yes, sir.
let
It is
me
lagging,
close.
sir.
Sound and that video is not playing
So
in
when we
a like coordinated manner.
compact one layer of sand over the other, both having
What we can do, we can again play this video from 37.27 and this timing. Okay, so 1 second. Sometimes because of network issue, some lagging takes place.
welcome to the Foundry of the boxes between
37.27.
surface of the to mark the
1
cavity.
minute.
Curves to
So
complaints of the
let
mold
me
box.
open the video.
Allow the moisture to the mold cavity box does not draw a bond with the core.
Okay, now it's okay. I will share the content now with include computer sound. Foundry.
Screw hole. Why screw hole? Because that is the hole for which we'll be pouring the molten metal. Next, we are going to place the other box.
Can you listen the video now, students?
Yes, sir. Yes, sir.
Yes, sir.
This
Okay,
box
just watch the video.
that is called the drag box. And the initial box into which we have placed the wrap pattern and wrap the sand mixture that was called the coat box. And if you can recall, and the sand, what we are sprinkling it on the surface is to ensure that the sand that we compact in the drag box does not draw a bond with the of the compacted sand in the coat box. The reason is the box is the first bottom box as it appears now in this configuration. That's a coat box that has binding material, and the other sand now what we are pouring it that also has binding material. And so when we compact one layer of sand over the other, both having some binding material, they will bond each other. We would like to deter these two layers of sand from bonding with each other. And how do we start the molding of the dark box? Initially, in the first box that we have done it, we are pouring
Now this is repetition work,
placing sand,
so I
because this
will
is the layer
pass
of
it
sand
on.
which goes to cut the cast or molding sand mixture, which are of uniform size, and which we attain it by using the pin end of the rammer. We start with a piece of lump using the tool, which is called a rammer. The function of the rammer is to ensure that the individual grains of the sand which are apart comma at the bottom. Next, using now, there are three words that you have. One is in English we have wire, other is rod, and the other is bar. So these words, if you try to geometrically identify, visualize what their shapes are, they're all cylindrically shaped. But then in English we have
Okay,
wire,
now please see one of
other
the
is
aspects.
rod, and the other is
Uh,
bar. So these words, if you try to geometrically identify.
Okay, see over here. Whatever cavity was present in the pattern, that cavity got made with the help of sand. Okay, so this part will take care of this cavity now. So how it got made? Directly by adding sand. So we call it as self core. That's why this pattern is called as self core pattern. Now this box will lie at the bottom, and this will be on its top, and we have to make the gating system over here, and finally we will get the final cast product.
Visualize what their shapes are. They're all cylindrically shaped. But then, what is the variation? What is the difference? The difference is in the diameter. The wires are those which are fine or small diameters. This shows how we have separated out the drag box. The pattern has a cavity in this, as you can see, and hence, when we go to compact the sand in the other drag box, that particular impression or that particular cavity gets developed or produced in the second box that we have done, or the drag box. This is what we are going to show you. This next function is we are going to withdraw the mold. I mean the pattern from the mold. Sorry, the pattern from the mold. And how do we do it? We run pattern a little bit so that it gets frees itself from the mold mixture, and then we use a tool.
See over here, this one is for riser, and this hole is for sprue. So now this, I said you this was scope box, and it should be placed on the top of that. So now he will place it on the top of that box. But before that, he need to make a gating arrangement so that this liquid metal from this sprue should get into this cavity.
The pattern out of the book. And the tool is called when I've used the sides of the passage. This no runner which was developed from the pattern itself. The pattern itself. So that is going to generate the cavity inside the pattern, and anything that we use in the casting process that goes to generator. It was made by the.
So what he is doing right now? Now he is placing this scope box on this drag box, and from sprue he is making the pouring basin so that liquid metal can be poured through it. Okay, so this will be on the top, and this was the position of riser. So he will make a small basin for riser also, so that the metal can remain over here. It should not flush out from the top.
The pattern itself, hence the pattern was called the self-put cut. This operation, what we are making it in the molten metal. Next, when we place over
See
the
how he is
drag
placing.
box, and after doing so, we place the cope box over the drag box. The third half,
now for split pattern, same thing he will repeat, but since this pattern is split in two parts, so one part he will make in cope, another part he will make in drag.
Here we can see, and the red portion is the portion faces of the equally fine to the party. The front after the front, and then with the windows of the table surface on the mold surface. This is sand into using second half guide pins.
Now what he will do, he will put this second part above this first part using this hole and dowel pin, so that both will get aligned, and then he will again fill this box also.
Misalignment between the gradually hole and the hole which produced by the use of the riser pin is called the riser hole. After placing the pins, we are going.
This pin is riser pin, okay, and this one is for sprue. So he fixed the location for riser and sprue, and then what he will do, he will do the same process again. So we can skip.
Fine layer of fixing and loose tool. The passport I printed out the halves of the
तर तो
and we
सिगरेट
can
के आगे
see
बिना गाड़ी
below how the pattern is compacted into the mold. Moving or withdrawing the pattern out of the mold is called the draw spike. Why draw spike? We run out of the mold. Half the pattern at the mold. The draw spike will be used. The cope mold to being used for cutting move for sure. It the one that oh, chal. Off করে দিলাম হ্যাঁ
So this completes your mold and mold making process for all the three patterns. Now what he did, he melt the liquid, he melt the aluminium, and then what he will do, he will pour it in this box. Okay, so if you see the white powder that he has sprayed just for some preventing some chemical reactions between this liquid metal on from the top, as well as it helps in easy flow of the material of molten material. So see what he used to do now. He's removing something. Okay. So that is basically called as slag. That slag formation takes place because of the reaction during melting between flux and the aluminium. So that slag he has removed because it is a solid part that will not help you in melting, and it accounts for as an impurity for the product. So he has removed. The name is slag, SLAG, slag. So he's removing all the slag. Once he remove all the slag, what he will do, he will pour pure liquid aluminium in this mold using pouring basin, not through riser, okay, through pouring basin. This is riser holes. You can see the shiny material coming out of from this. So once it comes out from this, you will understand two things. First thing is that it has got completely filled up through liquid aluminium, and now you can stop pouring extra material so that it cannot fall off the surface. So this is a furnace where you are melting the material. Solid aluminium is fed in this cupola, and what will happen, it will melt. Now melting, he pour it in the cavity, it got solidified. Now he removed both the boxes, and this is one of the mold box. What he will do, he will remove this sand portion from it, and he will take out the cast product. Second box. Since we are breaking the sand, so we call it an expandable mold. Why? Because you are crushing it after getting one product, then again you will make the same procedure, you will follow the same procedure, and again you will get a product. So expandable mold casting, we call it as. Now, students, you can see this is our final requirement. You were asking initially, like what will happen because material will solidify in every portion, in riser also, in cooling getting system also. So this is inverted image. He is holding the material through a riser. Okay, and this was the sprue, and below where somewhere will be the pouring basin, and this was the runner part, and this is your final cavity that you made using pattern, and centrally you place the sand, compacted sand called as core, that made the hollow portion. You got it? What you have to notice over here, everything is attached all together. Now you have to do some post processing. You have to remove this gating system, you have to remove this riser, you have to do some surface finish. There are some extra materials also that you have to remove, and then you will get your final desired product. So I think this much only. This is the top view of what you did. So from here you put pour the material, it went inside, and through channel it solidified over here. Now one thing also you have to understand, it will come in later slides. This shape of this sprue is tapered. Okay, so just keep it in mind, the shape wherever the liquid is flowing, we have gave a tapered shape. So this completes your video. So up to here it's okay to you, students?
Sir, I could not understand the design of the last mold. Were we making a cylinder with a hole inside?
Yes, we were making a cylinder with a hole inside.
Okay, sir.
So for that, how you will make a hole? You have to keep something so that liquid metal should not get into it. So that
Yes,
was
sir.
that's something we call it as core. Core is also a sand, compacted sand like mold, and we are placing it at the center. Okay.
Sir, it was inside the two wooden pieces. It was already inside the two wooden pieces.
No, that wooden pieces was used to make the cavity. So how core
Yes,
will
sir.
hang in the center? You need to provide some part
Yes,
on
sir.
the sand also, na, as a support.
Yes, sir.
You just think in your mind a simply supported structure in the center. So for that simple supporting from both the ends, we had some extra parts lying. So what you did, that black portion of that pattern that you saw there, there was a red part and there was a black part. That black part was the dimension of the core. Okay. So in this video, they didn't show you how they put the core. So they had a already made core. They know the for this lab they have made it and they are placing it in the center.
So core is
Okay.
made of a wood only.
Sand, same sand. No, that's not a
Sand.
part of pattern. That's a part of mold.
Yes, sir.
Mold
Yes, sir.
and core, though both are same thing. Just the difference is core is in the center for making some hollow structure. Okay. Pattern is
Yes, sir.
something which we are removing. It will not lie in the finer melting process. Just to give the shape and size of the cavity, we are using pattern. That part was not present, I think, in video also, like how he placed the core. That's why that confusion is coming. Now, can you see the slide? Pattern design, types of pattern alliances and pattern layout.
Yes. Yes, sir.
Okay. Now see, only 15 to 20 minutes slides is left. Just quickly go through them, and now it will be easy for you to understand. So pattern definition we already did. What is it? It is replica final
Sir,
product.
sir, in the video, the function of bellow has not shown.
It was not shown because no sand particle went inside the cavity. See, bellows are used to blow loose particles of sand from the mold cavity. So once the sand will fall in the cavity, they will remove. By procedure, they should use some bellow also so that they can clean the cavity portion, but they didn't showed it. You just get it like he did it. Okay. You got it? When the loose particle will fall na, in the cavity, then only he will use the bellow to remove it. So since he's doing it from last 10 years, it's not the case with him. But when students used to do this experiment, na, they have to remove some sand particles, because while making gate, some sand was getting inside that cavity. So for that we use below. Below here it is made of, in this video it looks in like a wood, but it comes in a rubber shape also. If you see in your laboratory, it is used for other purposes, for cleaning of a surface. Okay, it's a pump sort of thing, mechanical pump, where when you press it, what will happen? The air will flow at a high speed and it will remove the loose particles. Okay. So now pattern design. Pattern, you know about pattern. Pattern you used to make the cavity, but it should be slightly bigger than the final product. Why? Because of the contraction. I told you contraction can take place, as well as what happens, you are ramming also. You saw now, for taking out the pattern, he was putting a pin inside the pattern and then losing the particles and is taking it out. So for that also, what it causes, it causes the dimensional change. For that you have to incorporate it in pattern only. So it should be designed in order to easily remove without any damage done to the prepared mold. Same thing, every dimension variable. What patterns material we used for our experiment today? Anyone? What was the material of the pattern?
Wood, sir. Wood.
It was wood. Okay,
Woods,
so why we are using wood? It was easy to machine the wood, and it's like a good common pattern material. We can use some metal also, we can use plastic also. So for a lab demonstration we are using wood. And types of pattern, this he went through these slides in your video also. There he showed you a solid pattern and split pattern also. I think the third experiment that he did, there the pattern was split in two parts. One was in cope and the second was in drag. So that third experiment belonged to a split pattern. Okay, so if you see this cross section dowel pins, he explained in the video. There is a pin and there is a hole. This pin is called as dowel pin. It helps in alignment of the material. Then a match plate pattern. These patterns are like based on requirement. If let's say even after dowel pin the arrangement is not perfect and you need to arrange many materials at a particular location, for that they are using a match plate and they are putting both the materials on this match plate. And after casting, what they are doing, they are cutting down the extra material and they are getting the final products. Like you can add a lot of different patterns on same match plate. See here in this image, patterns 1 2 3 3 patterns has been arranged on same match plate. So this is also one of the pattern. Basically types of pattern depends on your requirement, what sort of structure you want to form. All structures cannot be made in same type of pattern. Okay, so which one is easiest for you, you go for that only. So cope and drag pattern, again same for split pattern sort of thing, where every arrangement is present in this only, like riser arrangement, and the riser location is fixed with the help of that pattern only. Now loose piece pattern. Let's say there is, just see this hatched portion. If there is some intricate profile which is difficult for you to make these loose, you what you will do? You cannot remove this. Once it is made now, you cannot remove this. Once you will remove, this sand will fall down or this will break from here. So what we are doing, we are making it in the form of loose pieces. It will remain at its place and you can remove this pattern so that this cavity will remain, and then after this cavity we will remove these loose pieces from these sides. Okay, that's why we had made it in loose part, so that you can remove the pattern in two ways. First remove the main part, then after removing, the cavity will form and then you will remove these loose pieces. Sweep pattern is something, let's say if you want to make a cavity, what basically pattern is doing? Pattern, all sorts of pattern is doing one thing, it is making a desired cavity. Whatever way you select to make the cavity, that will become one of the types of pattern. Here what we are doing, we are using a, let's say this is made of wood, this sweep, and you want to make a uniform circular mold of symmetric. there is a symmetry between this right half and left half. So what you will do, you will put sweep inside this and you will rotate it. Once you rotate it, it will remove the sand. After some rotation, remove the sand material, then rotate it again. So after a few steps, what you will find, you will find the cavity of the same dimension of this sweep. So we call it as sweep pattern. So this is also one of the aspect. Using this, you can make a symmetric kind of mold or the cavity. Now, after these, all these are the types of pattern. So we have to give some allowances in the final pattern. Why? Because I told you, I think we discussed before also, that when the temperature changes, that shrinkage in material takes place. Okay, that shrinkage you have to incorporate. Yeah, how much shrinkage for what material takes place. So through this diagram, try to understand whenever, what is this y-axis? It is the height of metal column. Height is decreasing means we are calling it as shrinkage. Okay, it is shrinking. Sorry. And this is the temperature. So when you pour the liquid metal, what is the temperature? Let's say this end is the point from where you are pouring the liquid metal. Now liquid is getting cooled. While cooling, you can see there is a negative slope. This slope means the metal is contracting. Once it reaches over here, the phase change takes place. From liquid, it becomes solid. So latent heat will get absorbed and that will form that phase change. During that, contraction takes place. And now from that temperature, once it solidify, it comes to room temperature again, it is getting contraction. So these contraction you have to understand. Okay, for this material, if I will pour at, let's say, 700 degrees centigrade, and it will come up to 25 degrees centigrade, what is the value of change in height? That you can understand through back calculations or through previous results. And you will say, okay, if I will pour 10 mm initially, it will become, let's say 8 mm. Okay, here we have exaggerated to make you understand it, but let's say it happens 8 mm. So you understand, okay, 2 mm, it will decrease. Let me pour 12 mm so that I can finally get something around 10 mm. So this is the way we are doing, we are taking care of the shrinkage allowance. See, in this sentence, solid shrinkage is taken care of by the shrinkage allowance providing extensions in pad. So once you make a bigger hole and after contraction, it will become whatever the exact dimension you require. So pattern should be bigger with respect to the exact material. This is okay to you? Now, draft allowance. See, he was removing the pattern. So while removing the pattern, now
Sir,
what happens? Yes.
sir, in the previous slide, the shrinkage is means calculation is based on heat and trial method.
Previous slide means this one. Which one?
Yes, sir. Yes, sir. In this slide, means the calculation of extra material is based on hit and trial, or we can have definite formula.
No, no. See, we have definite formula because let's say you are using aluminium. So aluminium, we are not the first one that is doing this experiment of casting. Lot of work has already been done on aluminium. Okay, so we know that aluminium. Let me move on. We have given that value or not? No, it's not there in this slide. What happens? We know that aluminium, how aluminium performs for the contraction. So what is the coefficient of expansion and coefficient of contraction of the aluminium? We know. Okay. So coefficient of those, if you know the values, what you can do? You can do the calculation. Okay, we are giving a 10-minute time for the liquid to contract, and that 10 minute is going from temperature T1 to temperature T2. Now, if you know the temperature difference and the time difference, we know that the coefficient of contraction of the material is such and such value. So by putting all those values, you can understand how much contraction will take place on that. So it's totally calculated value. It's not that we are doing heat and trial. although if you make a new product, a new material, let's say the material is very unique, and you are working on metallurgy and you made a new material. So for that new material, you do not have the value of coefficient of contraction. So you have to first justify the values of or the properties of those material, then you have to put it in the calculation. Got it?
Yes, sir. Thank you.
Okay. Okay. Now draft allowance, draft is the taper provided by the anyone want to ask anything?
Yes, sir. So I had a doubt. What is exactly the? I mean, why are we using the rising feed especially? I mean, we also have extra material in the sprue part and the gateway part, right? So will that not
Mhm.
suffice for any extra material required?
That is okay, but what happens when the solidification takes place, na? It is not so
Yeah.
that always the gating part will fill the farthest most point, the extreme most point. Okay.
Oh,
Let's say the gate is present in one side of your casting, or let's say the requirement of material is on the other side. So that liquid metal will have to flow up to there, then only it can fill. And in
yes.
that case, if let's say some solidification has taken place in the path of that flow, then it cannot fill those parts. So what we are doing, we are always trying to put the riser in such a way so that it covers all the part. So that's
Oh,
why riser is important. It's not
okay.
because getting will only be in the one end of the pattern. So
Yes,
that
sir.
part I think riser. See, riser, a lot of questions are coming. So see how we are keeping. Let's say this is one of the slide that we will cover. So riser, there is a side riser, there is a top riser. We have kept a riser in the extreme end because this pouring basin cannot always go and fill this cavity on the end portion. So a riser is like there may be more than one riser, there may be three risers based on the requirement. Okay,
Yes, sir.
draft
Got it.
is okay. Draft is the taper provided by the pattern maker on all verticals. See, you are removing the pattern from the cavity. So if it will be a perfect vertical wall, what will happen? It can damage the cavity. So we are providing a small taperness. That taperness will help you to remove the pattern, and that you have to take care of through some allowance. We call it as draft allowance. See, some values are given over here of how much draft they are giving by degrees and all those. If you see this figure now, you will understand. See original outline. This is the original part that you require. And what you are giving, you are giving some extra value to the pattern, that is 3 mm, let's say, for machining, because that top surface finish is not good. So you are giving extra material for machining. Then for removing the pattern, you are giving some allowances called draft. So all those will come into picture, and the final pattern that you will make will be of this external boundary, this external boundary. But our requirement was this hatched portion only. So we have to take care of various allowances in making of pattern. Okay. Now distance distortion, camber allowance. Sometimes some distortion takes place. Okay, while cooling, it happens that there is unequal stress in the material, and it will bend. So if you know that, okay, if I will make the pattern straight, so the pattern will get distorted like this. So in order to make this straight, what you will do, you will allow some deformation in the pattern only, so that after doing that distortion, it will become more or less straight. So you are taking care of everything in the pattern only. Shape and size factor, whatever you require, for that you give all the allowances in pattern. Wrapping also, like to take out now, he was hammering it. If you have seen, slowly he was hammering it after applying pin. So some allowances is given for wrapping also. Now riser feeder, lot of questions came from this. You can understand from this figure, the riser is very important, so that every liquid metal can reach or can be fed to all the this casting equally. It's not so that one portion will receive and another portion will not receive. So for that we are keeping risers also. And types of riser: open riser, blind riser, side riser, based on the requirement. Like what sort of requirement is there? See, open riser, whatever we showed you in our lab, that was open riser because that end was open. Okay. So if you pour liquid from one end, this is a blind riser, and after this it will reach to this sand. So this will also incorporate the whatever gases will get generated will get incorporated through this as well as through vent, and one of the riser is required for this portion. Why they are using two risers? Here you can see that that core is blocking that part. So I think in this figure, that's why they put two risers over here. So based on your pattern only, or the part you require, we are putting the risers. Blind riser means this closed one, not exposed to the atmosphere, and stays. What is the benefit? Metal cools slower and stays longer, promoting directional solidification. Means if it is a blind riser, it will help in slow cooling. If slow cooling, then directional solidification can take place and maintain heat longer. See the difference. Here it is written, blind risers are good design features and maintain heat longer than the open risers. A gating system, this you already saw, that pouring cup, sprue, pouring base, runner, and gate, so that it can enter into the cast material. So this is the overview of the gating system. What are the objective? First is to clean molten metal, so that if any impurity may fall below, it should get trapped. Sometimes in this bottom portion, sometimes in some arrangement called as skim bob, we are giving there they can get trapped. Smooth filling of the cavity. Cavity should get filled in a smooth way. There should not be turbulence in the liquid. Otherwise, gases will get trapped inside it. That is one of the objective. Uniform filling of the cavity, complete filling of the cavity. Okay, so all these will ensure through gating system. Parts of gating system, I think already you got through the various slides. Pouring basin, sprue. Sprue well is the bottom portion which has got a depression so that some heavier particles can settle down over here. Then the runner part and ingates. Creating a gating system, again, this is not required. See this slide. Top gating system and bottom gating system. Sometimes you can pour through a top portion. In that we call it as top gating system. Sometimes you can pour through side, or sometimes you can pour through bottom. So based on your requirement, I told you which one is better, they can select. So these are the differences basically between top and bottom gating system. Fit directly into the mold. This is what you were asking. But here what happens, that damage to that cavity takes place. So in our case, we were not going for this procedure, and we were using this middle gating system or parting line gating system. And in bottom gating system, metal enters from bottom to the mold cavity, minimizes turbulence, erosion of the, this is what I told you, minimizes turbulence and erosion in the mold cavity. Horizontal gradient that do not promote, but here the temperature gradient is not supported. Here the temperature gradient is much more supported in case of top gating system. This is something I told you to take care of while watching the video, that the shape of the sprue that they were using is like conical. Why it is so? Because when a liquid falls, it falls in that fashion. It makes a like a slant surface. If you make a sprue straight line, what will happen? Those cavities will be filled through air, and once air will enter inside it, it will create a gradient, pressure gradient, and what will happen? It will get enter into the mold, and once it enters into the mold cavity, it will form the pores. That's why what we do, we make it tapered so that air cannot go get inside the cavity. These are some of the formulas, like how they calculate the taperness of this one. Now core, core is a like someone was asking how you made that central portion hollow. That is made through a core, and if you see over here, a core is placed in the mold to produce a hole, undercut, or internal cavity, whatever you want to make. Cavity in the core box is a negative replica of the corresponding part. Whatever part you want to make, see this image. Here there is a pore. Sorry, there is a blind hole. This blind hole you want to make. So in the pattern, what you did, you made some arrangement called as core. This core will get inside and will prevent liquid metal, so that the replica will form, and there will be a hollow portion over there. Now these are some of the properties of core.
Excuse me, sir.
Types of. Mhm.
Sir, but if we put core in the sand, then sir, how can we remove the core out while putting the molten metal, sir? Because if we are, sir, it's like a complicated shape. Now, if we remove, then all the sand above it will also get removed. Like it's not.
See, core we are not removing. What we are removing? You can see the cursor right now. Okay. Can you see the cursor on the image, the central
Yes,
image
sir.
of this slide? See, you see a white portion and a central
Yes.
gray portion. So this central portion, gray portion as well as white portion, this whole portion was in the pattern. Like pattern was a solid of this shape. Okay. Once you remove the pattern, what we are doing, we are putting a sand, compacted sand of the shape of core. This this is actually sand. You do not have to remove it. Okay. It is a part of this mold. You are making a cavity to place the core, then you are placing the core. It is in the form of sand. When the liquid metal will come inside, it will fill which portion only? White portion. It will fill the white portion. And once
Yes,
it
sir.
solidifies, what you will do, you will break all the sand. So when you will break it, this will also get break, and you will remove it. Got it? Basically, core is also sand only. But to put the core, you have to make some arrangement in pattern. That black portion na, in the pattern, split pattern he showed you, red part and black part. That black projected part was taking care of this zone.
Okay,
This
sir.
zone, so that you can place it in this. It is hanging sort of thing. So you need to have some locations, simply supported locations for the core. Got it? So
Yes, sir.
core is basically
Sir,
sand
how
part
can
only. It's not part of pattern. Mhm.
how
Sorry.
can we make a thick solid sphere, hollow sphere?
Thick, solid, blind. Like from everywhere it is closed. Hello.
So I
Hello.
think he's asking for hollow sphere.
Yeah. See, for hollow sphere, what we are going to do is we are placing the core inside, and we have got some small supporting structures called as chaplets. What we are doing, uh, we are trying to support the core with some structures in the center. Okay. So once you support it with those chaplets, what will happen? That core will remain hanging in the center, and you have to make a position of pouring the liquid material. And once liquid material goes inside it, it will cover all the peripheral zone, and that core will lie directly, like on the center only. So you have to assume it like if you place something in the middle, and that should be hanging. It having hollow structure. So that hanging a small support structure in the bottom of the sand. Can you visualize? Let's say you want to make a hollow sphere. What you said, sphere? Anything. Let's take a cube, hollow cube. So what you will do first, you will take the external boundary of the cube, and you will make a pattern, solid pattern. It will remove all the sands from the center. Now you have to make a core of the internal cavity that you want to make. You place the core, but how it will hang? It cannot hang in the air. So from bottom you have to give some supporting structures, small supporting structures. It can be metallic, it can be of same metal, whatever you are going to cast, so that once it gets cast, it will dissolve. Can you assume it? Whatever I am like
Yes,
explaining
sir,
to
I
you.
got it.
So in that way, you can make some hollow sphere or whatever hollow structure you want to make. So types of core, again, horizontal core or vertical core. Those are the differences between different cores. Now chaplets, see, they are metal supports. Whatever you were asking, na, it can get clear by this image. Here the core cannot hang. So you have to give some supporting structures. So like this supporting structure will make it to remain at its place, and finally you can do the casting process. If you can remove the
but
core from this
we
part,
will remove them.
from this part, if you can remove it from this part and make it on the center only, then some more chaplets will be required for the support. Okay, it's a pin sort of thing, a small pin. So if you do not, you will get a, let's say, molten material flow everywhere, and it does not flow in the chaplet. So chaplet will be there in your final product. So for that, what we do, let's say the material that we are pouring is aluminum. So chaplets we can use of aluminum only, so that when the molten material will come, slowly it will dissolve. But before that, what will happen? Some solidification will start in the boundary. So now the support will be through that solidified material. In that way also we can make a hollow structure. See, it's written
So
over
then
there.
how we will remove
Uh-huh.
the sand which is in the center of the sphere?
That is an issue. Like how we will remove the sand that is in the center. So for that we need to provide some extra space. So what we can go, like we have to make a trade-off sort of thing. What we will do, we have to make some position where for some hole should be there, extra hole in the final product. And that hole we can fill through molten material at a later stage, like through welding. You can fill that using filler rod. You can fill those parts. Understood?
Okay, sir.
Like in that case,
Yes,
it's
sir.
not possible to remove the sand, na? So you have to do some trade-off. You cannot post processing should take place, and you have to fill that position. Chills. Now, chills. This is an important term. You should understand that cooling is like it not depends on you. The cooling of the material that takes place in the cavity. So, if you want to provide some directional cooling, you want some place where cooling should be fast, or the solidification should be at a higher rate. Some portion solidification should be at lower rate. Why you want different rates? Because that rates will define the type of microstructure formation at that zone. Ultimately will decide the strength or the properties of that zone. So let's say at some portion you want high strength, some portion you want relatively low strength. So how you will change that? You have one tool called as chills. Those chills act as the heat absorber or heat giver. Okay, so once for chills it is cooling, but for heating also we can use some different arrangement. So once you add some chill, what will happen? Just try to understand from this figure. This zone, we have added chill, so this portion will solidify at a higher rate. This portion will solidify at a higher rate. So the microstructure over here will be in such a way that this will have like more strength with respect to this and the center portion, or the requirement of the microstructure will be fine in this zone with respect to the center. So how you are ensuring that? By using chill, so that fast cooling can take place in these particular zone. Maybe this part, this zone is coming in contact with some other part where you require a fine microstructure so that it can withhold that part. Let's say it is a cross section of a bearing. So here what will happen? The balls will rotate. So you want different strength over here with respect to the center. So to ensure that, what you are doing, you are using some chill. Okay. So basically heat extraction, heat addition, this is the procedure. Heat extraction, if you can control the microstructures. This is again giving the same explanation. Now casting defects, this you have to understand through this figure. Like let's say you made a cast product and you can see these small bubbles over here. Sometimes you can see some top portion which did not get any material, like that. Like lot of different aspects are there in case of defects. So basically why defects occur? Because of gas. Sometimes some gases gets produced, those gets trapped inside, there is no proper ventilation available. So what will happen? Those gases will form holes, sometimes open, sometimes closed, and that will cause defect. You do not want porosity in the final product. Shrinkage you gave everywhere, you take care of everything, but let's say you missed some of the points, and because of that the shrinkage of material took place. Let's say riser was not at the correct position, so it made a cavity. That cavity is called a shrinkage cavity. Mold material defect. Mold material, what was the material that we were using? Green sand mold. Okay, so that material is has not got a proper combination of clay, water, and sand, and because of that, while doing casting, some part got washed away, some dropped, some penetration of metal took place inside it. Those causes mold material defects. Then pouring metal, like sometimes when you pour the material, what he did before pouring in the video, he removed the slag. If you do not remove the slag, that will cause the closing of the that screw channel, and that will cause the defect. Misrun means the temperature that you are pouring. Let's say you are pouring at a temperature which is just above melting point, so by the time it reaches the cavity, it gets solidified. So that was a pouring metal defect. So you have to keep a temperature so that it can cover everywhere, then only solidification starts. Metallurgical defects is hot tear and cold. This belongs basically sometimes when it gets contracted na. So while contraction, the material tries to pull each other, so during that period some cracks occur. We call it as hot tears. That is also one of the metallurgical defect. So these all sums up in this image, where you can see gas defects are there. Here cold shut, the temperature is not sufficient to fill all the cavities, so there is a white portion lying over here in the top and bottom, called as cold shut. Misrun, it started to pour, but it didn't fill all the portion. Some portion got left, and others, like this is you can understand from the figure also. And we have added some slides for each and every casting defects. You just go through it, and if you want to ask, you can ask related to any particular. But basically, if you sum up the defects reason, it is the this slide. These all are the reasons why different types of defects occur. The name of defect is there, and the slides related to those are attached. Okay. Now, just last slide here. Someone will ask, let's say you want to ask, okay, so you told about defect, but how you will understand which defect is present where? So first way is the common way, visual test. By seeing, you can say, okay, sir, I can see a pore, open pore on the top. I can see a crack on the top. I can see a scab on the top. I can see some portions left over from the top. So that is a visual test. Pressure test is specifically if you are making a, if you are casting a pressure device, how you will test? You will put pressure inside. If it can withstand your requirement, you are saying, you will say, okay, it's okay, there is no issue with me. Dye penetration test is a test where you are using a dye. Dye is something which changes its color when it comes into contact with let's say some holes or some cracks. So when you pour a dye on the surface, if the surface is totally flat, the dye color will be common, and if it has got some porosity in it, the dye color will change. So by changing color, you will say, okay, there is a porosity in it. Radiography test, you know about waves, ultrasonic waves, radio waves. So what are the properties of those waves? When the medium of the flow of the waves change, let's say a wave is flowing in air, then it comes in contact with metal, then it comes in contact with air. So what you are doing, you are changing the medium. So once the medium changes, na, the radio signal that gets a bounce back and you receive it, that signal will show different amplitudes. So by changing amplitudes, you can say, okay, there is a pore inside, you cannot see from top. When you send a radio signal, it will flow through the molten material, solidified metal. When it comes in contact with the gas trapped inside, it has got different density. So in that case, what will happen? That signal will bounce back and it will show different amplitude. When it will flow through a pure metal, it will show a different amplitude. So you will say, okay, there is a issue with this material. Amplitude is changing, so we can say, oh, there is some porosity in it. Similarly, ultrasonic test also, but the waves that we use for it is different, ultrasonic waves. So these tests will ensure, okay, there is a problem in your final product. Got it? So students, this completes our slides. So for theory part, we have to cover a lot of things. And defects part, I didn't went in detail of each and every defect. So if you can go through them and you can ask anything in chat box also. In future also, if you face any problem, you can ask about it. And related to some question answers are there in another slide. Those basically are the generalized question. Uh, if you want to ask something, ask, and just look on those slides also. Let me show you some slides related to questions. You want to ask anything? Anyone? Okay.
Sir, I have a doubt.
Ask.
Sir, you explained so many features, but most of them weren't used in the product made in the video. So is there any such thing that some features
Yeah.
are only?
No. What happened now in lab or lab explanation? We have got, let's say, 3 hours of lab to show you a product, and for that we selected intentionally the easiest parts. And since you are in the first year, so I think for basics, you need to understand those things first. And because I think most of you have not seen any casting process up to your first year of BTech. So since you do not have any background knowledge, so we try to show you the simplest lab experiments because it is time consuming. But for theory part, we try to cover different features also. Got it? So that in future, let's say if you get some curiosity related to casting and you go for some videos or you go for some book, it will be easier for you to understand, okay, we have these things are taught in the class, and you can easily grasp the topics. One more thing, the requirement of a customer for a product varies. Someone wants this, someone wants a small, someone big, someone wants in different shape. So to incorporate all those requirements, we have to have a broad like tools and techniques available so that we can made all those products. Got it? That's why we showed you different things, but for lab demonstration, we picked the easiest part. Okay, na?
Yes, sir.
Just see this slide, question answer, and we will conclude our class. Just see the questions. Name the material used to make pattern. We used wood. This was given in your theory also. What is core? It was in presentation. What is core print? Core prints are projections on the pattern that form and locate cores. Basically, the black portion that is showed in a split pattern. Red and black, two portions were there. That black part was core print. So this slide also we will share with you. Why are dowel pins required? You got the answer. What is master pattern? Sometimes we use one pattern, and with the help of that, we make duplicate patterns. That one pattern we always keep as an inventory, and we are using different duplicate patterns. Once a pattern gets disturbed, we are using another duplicate pattern using the master pattern. So this is basically a two-step safety feature. Like once a pattern gets disturbed, use master pattern. Then composition of sand we covered. What is green sand? We covered. And can sand be not? Can any type of sand be used? No. We read about the properties. Those properties must be present in a sand. Permeability we covered. green compressive strength. You just go through these questions when you get this slide, and I think we these things. These are the melting temperature of different materials. So this you can go through it, and why the metal with the gas gas should not be there because of porosity. Okay, so we covered most of the questions. Most means I think. So this concludes your class, and after 1 or 2 days, sir will share the slides with you. Okay. Hello. Anyone wants to ask anything?
Sir,
Anyone?
the video link.
Pardon?
Video link.
Video that will also share. Okay.
Okay.
So Ipsita, I think we have
Video link
already
I have
shared the
already
video
shared.
link.
Yeah, I've already shared in the
Yeah.
chat box. You can check it.
So I think this is okay. We can conclude our class. Ipsita.
Yes, it's fine.
Okay. Okay, all of you. Thank you. Thanks for being here for 3 hours, and in advance, Happy New
Thank you,
Year.
sir.
Try to study the slides when you get time, because in the end you will have to give a test. Okay. So that test, nothing will come apart from these slides and video. The format sir will share with you in a later date, whenever it will be decided. So thank you, all of you. You can leave.
Thank you,
Thanks,
sir.
sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Yes, sir.